Too loud. I think it's still a little loud. Okay, hopefully that's good volume. No worries, Visai. I appreciate you saying hi. Thunder, hello. Thanks for the work. Spetri, hello. And Davey, hello, hello. Thank you, Visai. Okay, so I think I'm good to go. This is my PDEs homework. I'm not going to do this yet. I'll probably get there at some point. What I want to start off with is looking through some academic papers. So I'm taking a class about cancer modeling, and we're going to have to do a final project where we take an academic paper and just kind of like modify it in some way and see what happens. So there's a decently long list of like suggested papers that would be good for this, and I just wanted to kind of like skim through them and see if I get any inspiration. So this is the first one I had in my list. Hey Lucas, nothing much. How about you? Okay, let's see if we can figure out what any of this means. Heterogeneity for IGF-2 production maintained by public goods dynamics in neuroendocrine pancreatic cancer. Okay, well, I know about half these words. IGF-2, no clue. Public goods dynamics. So some of these are game theory, and I think that must be a game theory thing. Let me zoom in a bit too, in case it's hard to read on stream. The hardest proof yet? Well, what was it for? The extent of intratumor heterogeneity revealed by sequencing cancer genomes, essential determinant, tumor progression, diagnosis, and treatment. Hey, Collarcone, listen to you. I'm listening. Multiplication for matrices. It's definitely super weird. There's a reason why it looks like that. I still don't have a very good explanation for it though. The song that's playing right now, it's Wham Bam Shang Lang. Who's it by? Silver. So I found a song through Guardians of the Galaxy. I think they used it in the first one. Oh, with summation. It is a title for sure. Yeah, if you write it with summation, it can be a lot to like figure out what's happening. Just wait to see the formula for the determinant though, Lucas. Like I wouldn't recommend you memorize it. Well, let's actually see if we can find it. It's like the formula itself is not very useful. Like it's not worth knowing, but it looks terrible. Here. This one right here. Or I guess you could also do that one if you want a summation with a big product. Think remembers that it's a polynomial. Oh, that's cool. This is dreams? I don't know what you mean by that. Oh, wait, oh, the song. Yeah, it is. Fleetwood Mac. Not an AI raid. You like this formula, Aeneas? I don't. Zach, thank you so much for the raid. I was lurking on your stream. Hope it went well. Destin, hello. Rex, hello. Looks like you're doing a good Thursday evening. Yeah. We were just looking at the formula for the determinant of a matrix because this is like it's not really worth knowing, but it just looks so terrible. Gold, hope you're doing well. What a determinant really means? There's an interpretation for determinant as like the area or volume of a like parallelogram or something, but I don't think it's all that useful to me, at least. Whenever you use some expression where finite group is neat. Fair enough. You'll take a chance in the near future and win. That's a good fortune. It's all on the test. For Twitch, you have to. That's true, Zach. But he says all on the test, but mine immediately goes to my PDE test I'm gonna have on Wednesday. I was like, if we get quiz on a determinant of a matrix formula on my PDEs class, I'm gonna like file a complaint. Yeah, so the plan for today's stream is I'm gonna look through some academic papers on mathematical oncology. I was kind of like going off on a tangent with the matrix stuff. I'm gonna have to do a project about mathematical oncology where we basically take an academic paper, change something about it, and then like see what happens. So I was gonna kind of skim through a bunch of the suggested papers and see if I get any ideas. I do remember that color code. We computed the derivative of the determinant. My math teacher learned about matrices. Noise. View it as an exterior algebra. That doesn't help me, Destin, but I'm sure someone can. Hey, Kevin. Maybe the real determinant was a Disney song they made about it 2 decades ago. I don't know that Disney song about determinants. Said matrices can be expressed as a derivative or something. Kind of confused about what he meant. I don't know about that. It's a derivative. So, like, color code was just talking about how you can... There is a way you can take the derivative of a determinant, but I don't know if that's what that's talking about. I don't know. Clonk. We estimate the wisdom of nations by seeing what they did with their surplus capital. It's deep. Wally? Okay, we can do that. We got a drawing about it? What is the derivative of the determinant? Max, that's a good question. You'd have to ask color code because I've technically calculated it, but I couldn't tell you what it means. Lemonade mouth? Yeah, I don't know that. Clunk, I hope your day is going well. Also spoiling in class. Take a number to a power of a matrix. Oh yeah, that's really fun, Lucas. Like, e to the power of a matrix is actually like a helpful thing. It's not you don't just do it for the memes. Actually, it just came up in my PDEs class too. Most name Italian was Cristoforo, one of the authors. Is that a fun fact? I don't know. Derivative of a matrix instead by derivative with respect to a matrix is a little more awkward. Oh, fair, yeah. Thank you, Clunk. Okay, let's see. Let's start working on Wally. Clunk was just drawing Wally, right? Let's see if we can do a better job than the Clunk. Oh, the answer to that is no. Okay, let's see. Paper color. Let's go with that white. That's not a bad white. When he was terrible learning French words. Sacre bleu. Okay. Oh wait. I just drew white on a white background. That's not smart. Okay. No pressure. I know. I've got an artist who has just drawn Wally, watching me draw Wally now. Wally. Eva. Exterior product is a function. I guess so. Oh man, I forgot about that emote clock. Wally is math. Mm-hmm. Epoustouflant? I'm sure I pronounced that perfectly. Um, I guess let's just there's nothing to do aside from getting started. I already messed up. Okay. Let's bring them a little closer. Oh my god, Dustin. Kind of look like glasses right now. I don't know if I'll be able to draw that. If there's a reference image that I can find, then maybe, but I won't be able to figure out what that looks like on my own. Does this baby come back? I do know that song. It is a good one. True. I think I saw her tell you that. That'd be the best at something, Suhas. Uh, you just keep working at it, but it's hard to be the best at anything. There's always someone better. So, like, it's productive to try to be the best, but don't expect to actually achieve it. In my opinion. Narrating to dating French girl with that accent. I would take it. Serves on Google Images? Okay. I, since we have two drawings queued up, I might have to go a little bit quicker than I usually would. Um, oh man, his arm is way too small. Don't worry, his arms are not going to be the same size, and that's okay. We're not going to make fun of him. Use perspective. If you think I have any sort of artistic talent, Suhas, you've got another thing coming. You're lucky there's even lines at all on this page right now. Need his treads. Carl doesn't want to introduce his Quebecan friends. Yeah, I mean, I am definitely down to meet some French girls if that's what's being offered right now. So, I appreciate that you think I could make a good drawing. Um, this is just for the memes. Hey, Leo. Now a math streamer owned? Oh, you're streaming now, Leo? Hell yeah. Tried a lot of things. Mostly of them fail. Sometimes after failing too much. I mean, yeah, that's how progress works. You fail a bunch, and eventually you don't fail. Why is his name tag not centered, by the way? Stream this morning and tomorrow morning, and then who knows, Lamau. Fair enough. The A is centered, that's true. And A is the first letter in the alphabet. Or doesn't have to be precise, just shows movement and emotion. You know, Destin, I like your interpretation much more. Oh, were you watching, Destin? I need to tune in at some point. I need to be better about checking my YouTube in general. Destin said I was cool, hot, and young. A little weird, but I appreciate it. You know, Destin's just a nice guy like that. At least if he feels like being a nice guy, he's a nice guy. I haven't listened to this song in so long. Okay. I'm just gonna get some color in this, and then we're gonna call this good because we do need to. Oh, that's a piss yellow right there. We're not using that yellow. Uh, maybe this one. That's better. We do to stream to YouTube and Twitch. Oh yeah. I need to remember the name of the plugin. OBS can't do it out of the box, so you do need to get a plugin. Oh, what is it called? Uh, OBS Multi RTMP. Right. Okay, I found it. I don't know why it's not in English. Uh, I swear it was in English when I downloaded it. Wait, view on GitHub. There we go. You can download it like just from like right there. So let me drop this link instead. Get the chat overlay. Yeah, the chat. Also, feel free to drop your Twitch name too. The chat overlay up there is from streamer.bot. Most chat overlays don't do Twitch and YouTube as far as I know. Add a screenshot, add that drawing. You want to us. Dawn is that fluent? We find deciding to go to the dark side Twitch. I mean, that'd be awesome. Forgot it wasn't English. That's how fluent I am. And thank you, Clonk. You know, this is not my worst drawing. I think my worst drawing is when someone made me draw a husky. I think it was Zach who. I think I'm maybe making it worse by adding this yellow, but I'm gonna keep it. I need a fill bucket. Is the issue. Remember the Taylor Swift? That was the Taylor Swift? I generally know who Taylor Swift is. I don't know what you mean by remember the Taylor Swift. Oh wait, oh the Taylor Swift that I drew. Sorry. Yeah. Okay, I remember now. Um yeah, that was a weird day. That's also up there for worse drawings though. My fave Master when he forgets he's American. What when I start trying to like speak other languages? Someone who speaks English only asked me for a math reference. I accidentally gave him a French article. Oh no. R2D2 or Wally? Ooh, that's a good one. Who would win that fight? Um, I feel like R2D2, like, doesn't he have, like, actually, no, I don't think he has a laser. Wally has the trash compactor inside of him, right? Maybe you can shove R2D2 in that. I think I'm taking Wally, because he at least has arms. R2D2 doesn't have arms. R2D2's only move is to ram. Lasers between his eyes. Imagine being French, it must be so hard. Okay, I think this is gonna be my Wally. Um, thank you, Zach, for the redeem. Let's see. Okay, so Dessen redeemed a Dessen d'enfant embedded on a Taurus. I might just refund it if I can. Oh my god. Uh, this is just a Taurus as far as I can tell. Okay, we'll just look up Dessen d'enfant math. Is there not a single image on here? Oh, okay. This is what a Dessen d'enfant looks like? That's okay. I mean, I guess that's easy to draw then. If you algebraic geometry got used to deciphering French papers, fair. Ooh, ooh, this hurts my eyes. That's a fun Dessen. Okay. Uh, this kind of looks like a chemistry drawing. Edre Goins? I'm sure that's how you pronounce that. Uh, what should I be looking for? Add Dessen, okay. G-Hive, old people at weddings always poke me and say, you're next. So I start doing the same thing to them at funerals. That's a good one. Hope you're doing well, G-Hive. This one here? Okay. That's not bad at all. First one? Okay, yeah. Wait. I pasted. Why didn't it paste? Okay, well, I just need to paste twice, I guess. Close, I'm all alone. It is so long. Okay. And then after this, we'll get back to the math. Can you cut it so it's bigger? What do you mean? Like, I don't know what you mean by cut it. So you can embed the pentagram on a torus. I think you can embed anything on a torus. Hey, Tenzini. Yeah. Trim the picture, focusing. Oh, I don't think I can. Like, I will only draw the torus part. I can't crop inside of this program though. You can't embed any graph on a torus? Why not? If you can do it in a... Oh, I guess that's the point of Dessins? Okay. Without crop... Okay. Fair. Oh, that's a perfect circle right there. You know, this is just like a donut. Dude, you could absolutely make a torus Dessin Donfont donut. Don't give ideas. Must be bitartate to satisfy the Belye map. It sure does, whatever that means. I agree. Draw Thingamajig says user Thingamajig 4000. True. Draw me like one of your French Tauruses. Tauri. Okay, you know, we have a ring all the way around the torus. Let's do that. Oh, no. Ring around the torus. Oh, God, this is so hard. Okay. Can we add pink cream on the donut? That's up to Destin's discretion, I guess. I wonder how you generate these images. It's probably a pain. Hey, you know, maybe I should send this drawing to, what was his name again? Ed Ray. And he can use it the next time he needs to present on this. This has some nice, like, symmetry to it, now that I'm looking at it, too. Can I get a Boston cream donut? I don't even know what that is. Yeah, mine is like 80 times better. Thank you, Leo. Okay, we'll do the little, like, nodes, I guess, and I think we'll call that good. Okay. Sending me asking for the Mathematica code. He refused? That feels bad. I guess Mathematica would make sense for how you make this without too much trouble, though. Boston cream donuts are amazing. I'd never heard of them. So at a bakery where we make weird motifs on donuts. There is a place here in Seattle called QED Coffee, and on their coffee bags they have like math like themes. Okay. I'm calling this a drawing and we're gonna get back to the math. Join the vertices from pre-images of 0, 1, and infinity in the Bellier map. Fair enough. Ugh. Mess up the screenshot. Oh, Suhas. You have outdone me, which isn't hard. But Suhas, GG. For 2 minutes, that's really good. Okay, got these uploaded to Discord. Gonna cash in these redeems. This is PD's homework lurking in the background. OBS GitHub is also in Japanese. I don't know. It's free and it works. So, you know, what more do you want? When will I open the Dawn Museum of Art? Soon, soon. Yeah, color. This PD's homework seems kind of cool, unlike some of the others. I have an idea for problem 4. I haven't been able to make it work quite yet. I haven't tried any of the others yet. But I'm trying to get an asymptotic expansion for like the fundamental solution to the heat equation. It feels like it should work, but I can't quite make the integration by parts give me what I want. WH is heterogeneity. It just means like differences. Like it's not all the same. Hey Eldritch, IRS and NASA on me. Yep, they're after me. Hope you're doing well, Eldritch. Try getting irrationally angry and punching the problem? No, that's a good idea, though, Leo. PDs does make me feel that way anyway. Well, good luck sending me that money, Suhas, because I'm not monetized on YouTube, so... Okay, let's at least get through the abstract. Can we challenge ourselves to do that much? It'd be nice, Suhas. The extent of intratumor heterogeneity revealed by sequencing cancer genomes is an essential determinant of tumor progression, diagnosis, and treatment. What maintains heterogeneity remains an open question because competition within a tumor leads to a strong selection for the fittest subclone. Ooh, interesting. Cancer cells also cooperate by sharing molecules with paracrine effects, such as growth factors. Heterogeneity can be maintained if subclones depend on each other for survival. Without strict interdependence between subclones, however, non-producer cells can free ride on the growth factors produced by neighboring producer cells. Oh god. I've already lost the plot. Collective action problem known in game theory as the tragedy of the commons. I honestly, I don't want to do game theory stuff. I feel like I should skip over the game theory ones. Oh, this is a banger of a song. I think you take Fourier transform in the x variables only. I just don't know anything about game theory. Oh, these graphics look sick though. Let me pull something up. Because last quarter I did that exact thing. Well, actually, no, I didn't. I didn't do exactly what you were saying, but I did something kind of similar. Matthew Patrick? No. Was it homework 1? This is the solution key for the homework. Oh wait, sorry, I know I'm not showing it. Uh, okay, so this is a homework from last quarter. We took the Fourier transform of the heat equation, and then we did an asymptotic expansion. This is just like one-dimensional. But the asymptotic expansion that we got, does not have a Gaussian inside of it. So I got confused. Campos is a good game theory course link. I mean, I'm not super interested in game theory to be honest, but fair enough. Transform the x variables only. Solve an ODE with respect to t to find the green function. I don't know. I want to just use integration by parts directly on like the fundamental solution, but it doesn't seem to work. That's not the way that I was hoping. I don't know. I do want to skim through a few more of these papers, though. I'm going to give this one a swerve. So there were, I think, 2 game theory ones. I don't know what the other one was. Optimization of dosing for EGFR mutant non-small cell lung cancer with evolutionary cancer modeling. Non-small cell lung cancers that harbor mutations with the epidermal growth factor receptor gene are sensitive to tyrosine kinase inhibitors, gefitinib and erlotinib. Catchy names. Unfortunately, all patients treated with these drugs will acquire resistance, most commonly as a result of a secondary mutation within EGFR. Because both drugs were developed to target wild-type EGFR, we hypothesized that current dosing schedules are not optimized for mutant EGFR or to prevent resistance. Well, this is cool. To investigate this further, we developed isogenic TKI-sensitive and TKI-resistant pairs of cell lines that mimic the behavior of human tumors. We determined that the drug-sensitive and drug-resistant EGFR mutant cells exhibited different differential growth kinetics, with the drug-resistant cells showing slower growth. We incorporated these data into evolutionary mathematical cancer models with constraints derived from clinical data sets. This modeling predicted alternative therapeutic strategies that could prolong the clinical benefit of TKIs. Let's scroll through until we see some equations. I'm concerningly far into the paper and I haven't seen a single equation. Is it gonna be one of these papers where like all the math is buried in an appendix? That's like a common thing with like a lot of the mathematical biology papers that I've read. There's not a single equation. Oh my god. There's not even one equation. Mathematical modeling. Two types of stochastic birth and death processes. Okay. Each PC9 or PC90R cell waits an exponentially distributed amount of time to divide or die, so time is governed by cell birth and death rates. Not so bad. PC9 cell replication, cell harboring. That mutation rises with given probability, mutation rate. Sensitive resistant cells have distinct growth and death rates that vary depending on the drug concentration. Ooh, these parameters were experimentally determined. Estimated the net birth minus death growth rate by fitting mathematical models of cells counts at 48, 16, 72 hours in the presence and absence of drugs. The rates were estimated from cell clearance assuming 50%. Okay, so this seems like something that I can work with. Let's go back to the introduction. Lung tumor adult patients eventually develop acquired resistance. The most common mechanism of resistance is a second site mutation within exon 20 of EGFR, observed in about 50% of cases. This change leads to altered binding of the drug within the ATP pocket. Currently, targeted therapeutic options for that are limited. Hypothesize that because clinically available EGFR TKIs were developed against wild-type EGFR, current empiric dosing regimens were not optimally designed to inhibit EGFR mutants in NSCLC, nor to minimize the development of drug resistance. Here we have identified differences in the growth kinetics of TKI-sensitive and TKI-resistant isogenic NSCLC cells. Incorporated these findings along with patient data into evolutionary cancer models. Generate mathematical models, predictive... Okay, this is a sentence I should actually pay attention to. Identified differences in the growth kinetics of TKI-sensitive and TKI-resistant isogenic NSCLC cells. Incorporated these findings along with patient data into evolutionary cancer models to generate mathematical models predictive of tumor behavior. So they grow at different rates if they're sensitive or resistant. So approach identified several strategies to improve the treatment of EGFR mutant NSCLC before and after the emergence of the acquired resistance. Okay, this one is possible. I'd have to like read it closer to have an idea for what to do with it. But that's a candidate to do a project on. Spatial heterogeneity in evolutionary dynamics modulate time to recurrence in continuous and adaptive cancer therapies. Treatment of advanced cancers have benefited from new agents that supplement or bypass conventional therapies. However, even effective therapies fail as cancer cells deploy a wide range of resistance strategies. We propose that evolutionary dynamics ultimately determine survival and proliferation of resistant cells. It was a transformative experience seriously. My god, syntax. Where is he buried? Hey, Anshu, I'm doing well. How about you? I do know yeah, he was a homie of Napoleon. Oh yeah. I remember learning this from physics and depression. This one on the left is the only surviving image of Legendre, and it's a caricature. Fourier was also drawn as a caricature, but we just have other images of him. Uh, I don't know anything about like actuarial math. I know what actuaries are though. We're seeing some question on electricity and magnetism. Ooh, I love electricity and magnetism. Same grave writer as Jim Morrison. Also went to Big Napoleon's grave. Oh, like Napoleon? um. Oh, hey, here we go. Wait, so did you actually go to Paris? Père Lachaise Cemetery? I've apparently been on this page before. His name's on the Eiffel Tower. You're there right now? Oh, that's so cool. Analysis of variance. Ooh, nice. Divyansh. Notable interments in the arts. Let's see if I know any of these people at all. Inescu sounds kind of familiar. Uh, is she a singer? Yeah, okay. I know Edith. Oscar Wilde, that sounds familiar. Author? Yeah. Richard Wright, that name sounds familiar. No Nightlife? Fair enough. There's Jim Morrison. There's Fourier. Who else is here? Comte. Philosopher? Yeah. Oh, he also did math, apparently. Saint Simon. I've heard of him. He looks a little like Malfoy. Like, he looks really annoying. Poisson? Well, I don't see his name in the list, but that's cool. Laplace? The Wikipedia page is missing then. Missing some important ones. Planning to pursue a master's in actuarial science from the UK. Ooh, good luck, Divyansh. That sounds awesome. Ramanujan Oradox theory? No, I never heard of that. I go to University of Washington, Divyansh. Control F? That's true. Poisson, nowhere. Laplace, nowhere. Frickin' Wikipedia. It's cool though. Syntax. It's Washington State, not Washington D.C. They're on opposite sides of the country, Divyansh. It is confusing. Propose that evolutionary dynamics ultimately determine survival and proliferation of resistant cells. Evolutionary strategies to be used with conventional therapies to delay or prevent resistance. Using an agent-based framework. Ooh, agent-based might be complicated. Model spatial competition among sensitive and resistant populations. Applied anti-proliferative drug treatments to varying ratios of sensitive and resistant cells. Compared a continuous maximum tolerated dose schedule with an adaptive schedule aimed at tumor control via competition. Between sensitive and resistant cells. No worries, Divyansh. It's a really weird thing. Like, we have two places named Washington in America, and they're nowhere close to each other. You saw Jim Morrison and Fourier? Fair enough, yeah. I did just visit Bruce Lee's grave, maybe like 2 weeks ago. And it's a nice grave. Recurrence is inevitable when applying continuous treatment schedule for a tumor with any pre-existing resistance. What is recurrence? I don't really know what recurrence means in this context. Let's do the same thing. Okay. Hey, okay, finally, this equation's on page 2. A red fish? Hey, quantum traveler, welcome in. Quick guide to model and major assumptions. Undergrad in math with minor actuarial science. Nice, Divyansh. Use an off-lattice agent-based model to investigate spatial evolutionary dynamics of different treatment schedules on heterogeneous tumors. Space limiting factors such as carrying capacity, cell enter quiescence due to contact inhibition. Oh, is that gold? I assumed it was red. Or do we call it gold and they call it red? I don't know. They got the physics equation in place. We usually have ads in Finland. Ooh. That's sick. No, Hanshu, I was not. Remember that from junior high? Fair enough. You think the Fourier transform method works? All right, you got me, color cone. Um, so I'm taking a two-dimensional Fourier transform in space. Is that it? Um, oh yeah, sorry, this problem is in C2, but yeah, like, and if it was n-dimensional. Oh wait, no, I'm stupid. It's an RN. Oh, I misread the problem completely. Jesus. Uh, and so, uh, the Fourier transform of the Laplacian, is that going to be n times ik squared? I'm not very good with multivariable Fourier transforms. Hey Yug, whatever that means, I don't know. Which for I know that you can do multivariable Fourier transforms. It's basically like an iterated Fourier transform. Um, and I assume that's what we need to do for this problem. Have I tried to debate flat earthers in a debate Discord? No, I wouldn't want to. That sounds like a waste of time. What do I think about your drawing? This, okay, it's really good, but it kind of something about it is unnerving. Well, let me show it. Like, this is really well done. Maybe I just don't like seeing myself. um, but yeah, like Nice. I can't look at it for too long though. I'm not much of a skibbity toileter, no. Oh, like Gordon Freeman? I'll take it. I haven't gotten that one. Accurate hairline? I have to look at the hairline now. Um, shut up, color cone. That is an accurate hairline, but I still resent that. It's me from Daisy. Yeah. Okay. It's like some k minus 2 pi pi sub k squared? Or what? This can't be it. Like you're telling me. Oh my god. This is true? I equals V over R? That's a good formula. Ohm's law is great. Hey, Skirtle. There's no way this is it. You know what? I think on my GitHub. Because for Navier Stokes, I actually did, or, well, I didn't. The professor did, but take the Fourier transform of a Laplacian. Multiplied by U hat at the end. Really? Quantum you know Skirtle and Jake? That's wild. Where the hell is Gaussian coming in math? Isn't that supposed to be physics? Oh, Gaussians are all over the place in at least certain parts of math, Yug. Jake is still tired. Yeah, I played P&W with them at least once. I forget how often. Fourier transform. Huh. That, oh, solve for x? Oh my god. 3 squared plus 4 squared. There's probably a trick there. I'm gonna do it the old... I can't do that the old-fashioned way. 84 squared? Yeah, I'm always super mean to Skirtle. Can take off the 84 squared. It still works. 9 plus 16 is 25. 25 plus 144 is... Wow. 169, which is 13 squared. What's the pattern? Well, when you add in the 84 squared, what would that be? I have no clue where that's coming from. But I didn't mean to... It's a Pythagorean triple. Oh, I'm not gonna know that. That is clever though. Also, hey Fembucks. Yeah, it's Avalon now. Avalon is fun too, but it's not the same. Um, yeah, Fembucks. I don't care. 85. That's a good guess, and it's right. Nice. Um, color cone Fourier transform with differential operator with constant coefficient to multivariate polynomial. Oh god, I'm not used to Nabla squared now. That's my preferred notation for the Laplacian, but now when I see it, it's just weird. I'm too used to delta. I'm also not used to seeing the arrows over the variables. Now it looks weird. Delta's... Why do you like delta more? I never did organic chem, though. I only did regular chem. They're doing a... They're also doing the minus A thing. I don't really want that. This, aside from the 2 pi, that is the same thing that you were saying, though, color cone. Why does this look weird to me? Oh, I know. Okay. I understand now. Uh I know why it looks like this. This makes sense. Oh, you have an emote, Fembox? That's sick. Yeah, sorry, Quantum Traveler. This probably looks complicated. I'm an applied math master's student, and this is a homework assignment. I was just playing Daisy on stream last night, but I also do these like math streams. You pass derivatives when I press what you say by IBP, right? Famished the integral. Um, du dt. Man, oh wait. I was about to use k as my variable. I'll keep using Kasai though, even though it's a terrible variable. Okay, so uh, color code is saying to solve this differential equation. Um, so we can just divide the u hat over here. Testing out my Kasai writing skills. Oh god. We're integrating in time. These are basically constants as far as differential equation is concerned. Well, f of x. Well, I guess like this. And then we want inverse Fourier transform. What definition did I use for the Fourier transform? I guess no 2 pi, so we're going to need the 2 pi. I think it's going to be the same. Let me grab it from my complex variables book. Telescope and Pythagorean triples. I have not seen that before. That was a new one for me. Use the convolution theorem. Oh, because this is the product of two Fourier transforms. I forget what we want our bounds to be, 0 to 2 pi or minus infinity to infinity. But Rn, that makes sense. I need to wait. Well, I need another dummy variable. Uh, or why is this? No, I'm integrating in Kasai. I guess vector Kasai. Is that it? Oh, it wouldn't be hat anymore. I do need hat. Oh no, I'm just the Gaussian bit. Okay, and I know that Gaussians are still Gaussians, but you get a factor out front. We're gonna have that factor to the power of n, I guess. Uh, there is. I have it written down somewhere. Thank you, complex analysis class. I think I found the page. Oh, is that Laplace? I don't want Laplace. That is Laplace, I think. Oh, here it is. Okay, so we had... Oh, this isn't the exact thing that I wanted. The formula I have written down. I don't think this is right. I don't think it's I don't think it's what I want. That hat f times g is hat f convoluted half g. Uh, well, right, but what I have is f hat g hat, and I'm hatting it again to invert it, right? And so I have like f hat hat convoluted g hat hat. So I I think this is right, isn't it? Oh wait, oh, do you mean I need to invert this before I put in the formula? That's what you're saying. Okay, okay, okay. Let's just Google it. Tuna melt. Ooh, nice. Enjoy. No white bread? Smart. After what happened last time. I don't know if that's what I want. Ooh, this looks like it. What is this table? For ordinary I'm gonna assume ordinary frequency. I don't know what the difference between these is. Never looks like the characteristic function of the normal distribution. It probably is, yeah. Hey, Henry. Sync? Oh, I've seen that before. I think it's sin x over x. Yeah. I think some people just comes up so often they gave it that name. Um, thinking of the Fourier transform cannot get consistent definition. Yep. My like my PDEs professor was literally he was talking about Fourier transforms for the heat equation, and he said that he's going to get the constants wrong because he doesn't feel like or like he never gets them right. So he just said to like look in the book if you want to see it with the right coefficient. He just ignored the 2 pi's entirely. Um, you claim your computation are right. Yeah, yeah. I see you did the same thing when we're talking about distributions. Um, Does that mean it to be 2n? Or no, hey, Grandmaster of Memory, welcome in. Maybe there's even an n multiplying out front. Seeing Fubini. Maybe let's just work on it for n equals 2. Okay, I guess, so on the inside integral there, we get root pi over t e to the minus pi why yeah, yeah, that's what I'm missing. I that's why I was getting confused. E to the I might need a negative? Is that how it looks? We just wrote this. 1 second. I don't think it looks like this. It should be psi 1 times x1, I think. It shouldn't be foiled out. I think that's better. So actually, I do want that formula that I wrote for my complex analysis class. You can do magic. So wait, the formula that I wrote minus infinity to infinity. Wait, plus why is omega and k not the same in Kasai? Oh, I think they're just being more general. They'll be the same for us, though. Dude, what definition for the Fourier transform were we using in class? Okay, for the inverse, it is 1 over 2 pi and e has a negative. we just plug in negative omega then? I guess we do. It gets squared anyway. It doesn't matter. I think my letters are reversed relative to the situation that we have. I'm so bored with this fucking formula. I want to do something else. Um, this is like, ugh. Okay. I just need to figure this out. Okay, we're integrating in Kasai. Let me... The x and however written down is the Kasai. Oh my god, let me... I'm gonna write down the exact thing and not try to fix the letters yet. Because I'm getting confused too with the vectors. Because this is just for one dimension, what I have written down. We can make it one dimensional though. Right. Because these can be completely split up. Terrible, Kasai. Ugh. Okay. Now we need to mix and match. So my k is root t. My omega is negative x1 or 2 or whatever. Root pi over root t e to the minus x1 squared over 4t times root pi over root t e to the minus x2 squared over 4t. Okay. And I'm going to write that as 2 over 2. It's a little bit extra, but it's going to be, like, indicate how the formula should look. Okay. God. What a pain in the ass. So, all of this was so I could fix this. So it's just any sort of convolution. So, pi over t to the n e to the minus magnitude x squared. I mean, I don't know which variable we want to, right? I don't know like which one should have the convolution. N over 2. F of y minus x dx. Oh, I mean, yeah. You're yeah. If I write u of x, I should do it the other way. True. I just assume it's better to have the comp or like the x in that, but I don't know. So like what I really want to do is integration by parts. I to get like some t's in the, well, I guess we already have some t's in the denominator, but like I want to show that like um you think we're done? I don't think we're done. We need something to first order. Like I think we need a series of some kind. No, I definitely want another step. Like, because like this I figured out, well, I didn't figure out this exact formula, but like I I guess I did. Except for the normalization. So like what I want is like if integration by parts and multivariable is the same as with single variable, what I would want is this like boundary term to be something with a Gaussian that'll be my leading order term, and then I want to show that the integral part is like little o of the part before it, so it's an asymptotic series. Um, the boundary part should be 0. The way that I was doing it, so I just made n equals 1 just to play around with it. I integrated f. And I think that, so it's gonna have, it no longer is gonna have compact support. You ignored the original question? I've been known to do that too. So yeah, I'm trying to get a series out of this somehow. I mean, maybe I should just directly do a Taylor series for a Gaussian. Would that might be the play actually. And as long as I can interchange integrals and summations, which I think is safe to assume here, I think that'd be easier than integration by parts. How does that look? Because we can just, like, if we can, uh No, a Taylor series can't be it. I'm sorry. Doing a Taylor series would remove the Gaussian entirely. That's why I wanted an asymptotic series, because that can include Gaussians. Never mind. I don't know. I feel like I know what I want. I just can't get it. That's like that's kind of the tragedy of life. What do you think is the precise statement? Uh, that u of x comma t is equal to um some constant times basically magnitude of x squared over 4t divided by t, I assume to the 1/2 or something like that power, plus little o of 1 over t to the 1/2 e to the minus x squared over 4t for large t. That's the sort of thing that I'm after. Really, Pooey? Is that not just making it harder? Lacking remorse? Thank you, thank you. Single and ready to mingle. I don't know. Problem's annoying, so I feel like I'm so close, but I'm just a little bit short. Hmm. What change of variables did they do here? It's gonna be something like what Pui was saying. I guess they did z equals x over 2 root t. What would that buy for us? Convolution of f density for normal distribution E equals 0 covariance matrix like t to the n over 2 or something. Yeah, this definitely has like some type of probability interpretation. The heat equation is kind of linked to probability as I understand it. Oops. DZ. Well, this. So. Oh. I don't know what this does for us. I forgot the Jacobian as well. Whatever it's called. Are you just going to show me the definition of asymptotic sequence or series? Yeah, basically. That's all the thing. This is basically the same thing as what I wrote with the little o. Hmm. What difference between you and the Gaussian with some scaling and bound the error term? Sure. I that I'm just not quite sure what power of t goes in the denominator. I don't know. There's probably a pi somewhere here too. Less cowbell. No, more cowbell. Always. The heat equation preserves... Yeah, it preserves energy, basically. Or like... It... It preserves this quantity. I think you said it better. Yeah. The mass of the fundamental solution... Yeah, it's 1. So we were doing tricks where, like, we consider u minus something, and we multiply that something by a thing that integrates to 1. Preserve D's. Hey, Boston. Hope you're doing well. Ooh, I like this song. I don't think I've heard it before. I'm doing all right. Thanks for asking. Glad to hear you're doing well. U of x equals e f of x plus bt, where bt is Brownian motion. Sure. Whatever that means. I guess you did. My text was using big phi. Wait. Uh, int rn. Oh, okay, sure, because that equals 1. Wait, what? Uh, no, I don't get what you're doing, color cone. Use is gonna be f star phi. But then what I already have a phi here, and this thing you said, like, for C is basically also phi. I don't get your setup. If you have Chinese food, you also have a brownie in motion. It's worth it though. Chinese food is so good. Gaussian the same mass. I guess it's not. Okay, wait. You're saying, so on this U, I'm so okay. I'm gonna write what I think you're telling me to write. 'Cause I feel like there's no way that this is helpful. But then this u is also f star phi. Like, I'm I'm really confused by what you're trying to do with this, I guess. This is a banger of a song. We can take int rn f of x dx. Okay. Maybe that's... Wasn't this going to be 0 now? Well, I don't know. Your C is total energy. I guess maybe it's not exactly 0. We can't necessarily bring the phi inside of the integral. Well, yeah, we definitely can't. Because this is just a number. And this is a function. Can I, though? I don't know why that got automated, Leo. No, I only do like those automated messages and then just like some like general stuff like exclamation point Discord. Nightbot for YouTube is really Nightbot in general is pretty basic. It's really intense. You couldn't tell because it's all truly, yeah. You have some initial distribution f of temperature, making a Gaussian solution with the same initial energy. Would it be helpful to actually plug our Gaussian in? I just have this memorized apparently. Did I get it right? I did. Look at me go. You know you're in a PDEs class when you have memorized the fundamental solutions of the heat equation. This is a good song. Okay, so you want to bound this in some way, color cone? For large T. I don't think I've heard it. David Lee Roth. I don't think I've heard of him either. Um, we could make this integral in terms of y if we wanted to involve these two integrals with each other just for fun. I don't see where that's gonna become helpful though. Old Van Halen singer. Oh, nice. I don't know. Semigroups, I don't think we're going to need those for this problem. Okay. Total temperature is preserved. Okay, the way we wrote the total temperature is preserved is to say d by dt Rn utx dx equals 0. I don't know if that form is more helpful. It's probably not. I don't know. I might look at a different question instead, because I feel like I've been banging my head against this one for long enough. Problem 1, I think, is kind of doable for me. I know the answer is just going to be like the equation for a line. It's going to be just y equals x, but with these boundary conditions. It's just making the actual argument for this integral that might be tricky. Where are my notes on Dirichlet's principle? Oh, I think he just wants us to derive the Euler differential equation, basically, which wouldn't be that bad. Okay. Let's bring number 1 in. So same for the music? Hell yeah. Is there a guideline to read theorems on my test? There's going to be a proof about the fundamental theorem of invertible matrices. I'm having a hard time understanding or reading proofs in general. You just have to get used to it, unfortunately. Like, with reading certain things in math, I feel like you need to be like a lawyer with how carefully you interpret the wording. And like when I first read a theorem, I need to think about it pretty hard before I understand what it's actually even saying. Yeah, it comes with time, basically. In proofs, you gotta read a lot. And even once you've read a lot, once you switch to a different part of math that you're not used to, it's like you're gonna start again from 0. Suppose. Then for phi of x with phi of 0 equals phi of 1 equals 0. And for all t in R, the energy of U plus T phi is greater than or equal to the energy of U. This represents like U is the optimal path, E plus T phi is a deviation from the optimal path. You prove everything you read. I mean, that's the Chad way of reading math. Math major, gotta know what's happening inside their brain. I doubt even a math major could tell you what happens inside their brain. Usually not the best at communication. Equals 0 for large T, because it has compact support. Art, thanks for the follow on Twitch. An approximation to get an approximation of U. Thank you, Femvox. Just Spotify doing the Lord's work. The thing is, so I want to bust the Gaussian outside of the integral. That's pretty much my only issue with this problem. I'm worried, like, I guess it depends on how you're saying I should approximate the Gaussian, because like I could bound it above by 1, but then my answer won't have a Gaussian in it, so I don't feel like that's making progress. Or even like a Taylor series, but so yeah, I don't know. Actually, what if I did the convolution on the other variable? That might actually save this. Or the other function. Well, no. What am I doing? I don't know what I'm doing. Oh, Gauss, his name is all over math. Get used to seeing his name. He's one of the there's a very good argument that he's the best mathematician of all time. So there's a lot of things that are named after him in lots of parts of math. You want to think of that monkey swimming? I don't know that reference. Um, Fly Me to the Moon. It is a similar song. It is that it's that's kind of sick that a monkey is swimming. I don't know why that's a meme though. Matt Hermatics invented math and trigonometry. Oh, Matt. Wow, Lucas, I didn't know that. That's crazy. Top 50? How extensive is your list of favorite memes? We need a list of Vosson's all-time favorite memes. Yes. Analysis. Okay, so let's take the derivative with respect to time of this bad boy. We're going to interchange derivatives and integrals. Could actually be a name. Yeah, it could be, yeah. Okay, then chain roll that bad boy to u prime plus t phi prime. Chain roll again times phi prime dx equals 0. Something, yeah, and analyze it wouldn't be that perplexed. Yeah. When you can see that trident symbol in math? Oh, this letter is it's called phi, Greek letter, or phi, some people say. There's one that looks way more like a trident. It's a psi. PSI. I didn't see them. Maybe in a differential equations class you would see them. Someone with a fat lip said it. It kind of a style thing. So some of my professors really like those two Greek letters. Others don't for some reason. Yeah. Random matrix theory? A little bit, Felix. It's way more interesting than I thought it would be. I've done... The only thing that I've done with it is it's called the range finding algorithm, where you randomly sample columns of a matrix to get an approximation for the column range. Oh yeah, true. Those are nice used for angles. Oh yeah, Lambda is a popular one too. Lambda might be one of the first Greek letters that I encountered. It's common for eigenvalues. You never seen lambda? That's crazy. Lambda is so common for me. Marchenko, Pasteur, and Stieltjes transforms. Stieltjes sounds kind of familiar. Exactly. Lambda is also the valve symbol. Meow meow. Yeah, Mew. This looks like a different thing. Oh god, this is a few too many symbols for me. Alpha, beta, gamma, delta, epsilon, pi, and theta. Yeah, those are some of the bangers. It's with Fourier? Like, this is a Fourier transform? Like, I'm seeing hats and script Fs. Digamma nuts. If you do programming, you know lambda. Oh, for like lambda expressions? Sounds like he's meowing. You have not digamma. How does it even look? I've seen a digamma function. But I don't think digamma is an actual Greek letter. Oh, it is. It's an archaic letter. That's why it's not listed. Huh. Wow. It was already deprecated in ancient Greek? Wow. Wow. Even. It's the derivative of the logarithm of the gamma function. Huh. This is the only context. Well, they don't even use the digamma letter. Base code of all symbols is E. That's a good choice. We're even using Greek letters. I assume because of Euclid's book, The Elements, was like the math book for over 1,000 years. Oh, nice. Leave the eigenvalues alone. Classified material. This seems like it's a little more casual, which is fun. What are eigenvalues? That's a great question. It's gonna be okay. So the first thing you need to know with linear algebra, do you know what a linear transformation is? Basically, so you can think of a linear transformation like I just made up a random matrix here. You can think of it as, so these are our normal coordinate axes, x and y, and we usually think of it as like you can go in like if you want to get to the point maybe 4, 3, you would go 1, 2, 3, 4 in the x direction and 1, 2, 3 in the y direction. but instead of doing that, actually, let me make this a little more interesting. There's no reason we have to travel along the x and y axes. We could have also like take these vectors as columns and or take the columns as vectors and travel along those. So 1 minus 1 is a vector like that. 2, 3 is a vector like that. This is not to scale. And so I could travel along. I should have given myself an easier combination to figure out, but in the same way that I was traveling along the x-axis and then the y-axis, we could also travel along these two vectors. So like maybe I start out by coming down here by reversing this one. Yeah, you can link it. And then we travel along this one as our path. And so that this is not what an eigenvalue is yet. But you need to know what this is before we can understand what eigenvalues are. We are in dire straits, Pui? Why? Okay, so good. And so kind of more generally, rather than thinking about a single point, you can think of a matrix as transforming this entire plane at once. So like, instead of our x and y axes being the fundamental thing that we use, we have like these as our axes. And they're no longer, like, these are no longer right angles, but that's okay. The thing that eigenvalues and eigenvectors tell you, I'll just spell them out here. They tell you what directions do not, or I guess like what vectors do not change after this transformation, aside from scaling. So basically, like, what vectors are pointing the same way? Because in linear algebra, we only really care about direction. Scaling is not a big deal. Inquisition, thanks for the follow. And so what you'll find, like, what, I don't know what the eigenvectors for this transformation are, like a span. You can talk about the span of the eigenvectors, and I think that's your eigenspace. It's not exactly the same though. It would be like, it's a vector. There's if we took this matrix, I don't know what the eigenvector is, but pretend it's like 1, 1 is our eigenvector. If we did this multiplication, we might get like 2, 2 out. And that means 1, 1 is an eigenvector. Because like this is dependent on this. Like they're basically the same vector. This multiplication is almost certainly not right, but like that's what the idea is. And so we can actually find it. It's basically, if you have a matrix A times a vector X, we're interested in when this multiplication results in a scalar multiple of our same vector that we gave it. So lambda is the eigenvalue. We don't know it yet. And then X is going to be the eigenvector. I mean this x2. Oh, I haven't seen that, Felix. I'll look at your posts once we're through this. So we can kind of mess around with this equation and see if we can find any x's that satisfy it. So I'm going to subtract this over to the other side. Equals 0. The eigenvalue could then be seen as a multiple of that matrix. Not of the matrix, only of the vector. Basically, like, we're looking for a vector x such that multiplying this matrix A only makes it a scalar multiple. Like, it's not really... It's like a special vector. And so we can factor x out of this, but we have to be careful. Factoring isn't as easy in linear algebra as it is with regular numbers. If we factor the x out, it comes out on the right side because this is both a right multiplication, and lambda gets multiplied by the identity matrix I. We should take this. Oh yeah, true. There's a lot of really good applications for eigenvectors. And so if we want to figure out what lambda is first, we can take the determinant of each side. Is that what we want to do? I might have this slightly wrong. I'm worried about this x vector on the outside. Oh, about the intuition? How else can I say it? What's a good... Well, what is... Can probably see the pure math computation behind it. Okay, so... Yeah, the intuition is definitely important. Okay, so thinking about this matrix here, all it does is it swaps the x and y values of your vectors. So if I give it 1, 2, I get back out 2, 1. But... And so, like, you can maybe imagine, or I'll draw it out here, that if we swap the x and y values, it's kind of like reflecting across the line y equals x. So 1, 2, it was up here, and then after transformation, it went down here. So it kind of got like pushed straight across. That's a weird way of saying it. Pushed, but like it got reflected across that line. But if there's like a special thing where if we gave it a point on this line, it will just stay put, right? Exactly, yeah. So if I gave it 3, 3, I would just get 3, 3 back out. So it's vectors that are basically unchanged after this transformation. This one, I guess it only has one eigenvector really. So just from this kind of like visual argument, I would say that the eigenvector for this matrix is 1, 1. You could also have said the eigenvector is 2, 2. The scaling isn't important, but anything where y equals x, basically. You'd also say like -1, -1. A globe. The x it spins on is an eigenvector. Ooh. That's cool. So, I assume that's what your confusion is about, where like the columns of this matrix don't inherently have anything to do with the eigenvectors. Like, you do use the matrix to figure out what the eigenvectors are, but you can't just like read it off directly from your original matrix. It's like the column space is very different from the eigenvectors. Eigenvectors are about input and column space is about the output. This may be the best way of saying it. Like eigenvectors ask about what vectors you can give a matrix. Column space is what vectors you get out of a matrix. Is it 1 -1, Felix? If 1 -1 is right here, it's gonna get. Oh, true. There are 2 eigenvectors. Ha. Okay. Okay, yeah. So there's actually a second kind of symmetry along the line y equals -x. So if I give it a point on this line, yeah, exactly. Like it gets reflected across, but the direction is still the same. Like the slope of the line is still the same. True love is not something that comes every day. Follow your heart. It knows the right answer. True love. Oh, you're leaving, Clonk. You're not a fan of true love? Yeah, thank you, Felix, for pointing that out. It's symmetric. Oh, yeah, Aeneas, I forgot about that. It is symmetric. It doesn't exist? That I'm surprised to hear that from you, Clonk. There's 2 eigenvectors. We can actually calculate them, but you could say they're 1, 1 and 1 -1. So there's 2 different directions where vectors are unchanged. Part A for the last question. I didn't know you felt that way, Klong. I'm learning. Like the way to make the statement precise? Color cone? My idea of the precise statement, like this is what you and I were talking about. The thing that I originally wrote was e to some power, and there's also like some constant out front. Little o for t to the alpha plus 1. Something like that is what I wanted. Oh, you're talking about this thing. Okay. One eigenvector is just the entire span of vectors. Yes. So one eigenvector is for y equals x. The other eigenvector is for y equals -x. Those are distinct directions, basically. You're able to bound this by essentially the gradient of phi by something that goes to 0 for t to infinity. When Here Comes the Sun is playing, true. um, gradient of phi res x? Uh, okay, let me finish talking about eigenvectors first, and then, or let's just like try and finish that up if you don't mind. Um, and then I want to see what you're saying. If you only care about direction slash lines as a projective space, eigenvectors are just a fixed points. Eigenlines are exactly the fixed points of the induced map on projective space. It's a little bit beyond me. You can see an eigenvector kind of like a function. A function is like finite points, infinite points, which have the same property. Uh, I think so. And I had never thought about a function like that, but I think what you're saying makes sense. It is like a family of vectors. It's not necessarily just one or two vectors. And as Anya says, that like yeah, it would be an in eigenspace. So like it's like okay, so you could say this is like these two vectors here are the basis vectors for your eigenspace. And you could choose other basis vectors if you wanted to, but I think that's kind of the relationship that uh is happening here. Exactly, yeah. It's just whatever space your eigenvectors span. Okay, and also I did say I'd look at Felix's blog post. Sorry that I forgot about that for a little bit. And then I also want to hear what ColorCon has to say about this problem. No, you're good, Lucas. Oh no, there's a small typo and I can't unsee it. It's okay. Writing is hard. 5 minute break. Okay, let me know when you're back. Color cone. Even saying you make typos, you make typos. Yeah, I mean, that's a really good point. It is proof that you're not using AI. I respect it. Oh, nice. Yeah, I never have done this kind of in general. Type O. Nice. Or wait. Oh, okay, okay. Never mind. I see what's happening. I did not know about this average value of the diagonal thing. That's kind of cool. I can imagine this would work because of the relationship between like eigenvalues and trace indeterminate. Wasn't the best in school, but your blood is always A plus. Hell yeah, Clonk. Oh, I get why it's the average. Yeah, it comes from that formula. Um, I mean, I can see it for 2x2. For higher n, I don't see it because that formula is more complicated. But yeah, the quadratic formula does give you the trace divided by 2, right? So that it just works for 2x2. Well, then why are you saying it works for all n? Or does this? Oh, okay, okay, okay. No worries. That is like neat though. I never thought about it as the average of the diagonal. Yeah. Thank you for linking that. It is hard to write about math, so no judgment. Okay, um so yeah, Lucas, if you want, we can do a calculation for the eigenvalues or eigenvectors, or do you have another question? I can. Oh shoot, sorry, you were asking about the post. I missed that. If the eigenvector is 5, 5, and lambda is 5. No, no, no. Uh. So no. You calculate them separately, Lucas. It's not something you pull out of these vectors. You actually get the eigenvalues first. Um. So let's just actually do a calculation. So coming back to this part here, I subtracted the lambda x to their side, factored x out, and I forget the exact justification for this next step, but in order for this to be equal to 0, we're going to require that the determinant of a minus lambda I is equal to 0, because x is any vector in general. So it should be this chunk here that is somehow equal to 0. I forget why it's determinant, though. And so this is kind of like the formula that we want for eigenvalues. I need more room. Actually, no, let's apply it. What did I just do? Why do you keep on doing that? Okay, let's try it with this matrix here. I don't know what we're going to get out of it. I hope I chose a good matrix. Oops. Okay, so I'm going to take this formula and apply it to this matrix here. So first, a minus lambda I, not thinking about determinants yet, is 1, 2, minus 1, 3, minus lambda times identity. And so 1, 2, minus 1, 3, minus lambda 0, 0, lambda. And then we just subtract them element-wise. So 1 minus lambda, 2 minus 1, 3 minus lambda. This is a matrix you want to take the determinant of. And the shortcut is you just always subtract lambda off from the diagonal when you do this. So you don't need to do this entire process each time, but I just wanted to show it in full. So the determinant of the matrix we just found, 1 minus lambda, 2 minus 1, 3 minus lambda, AD minus BC, so plus 2. And we're setting this equal to 0. So this is just going to become a quadratic function, and we know how to solve those, hopefully. 1 minus 4 lambda plus lambda squared. Oh, sorry, 3. Plus 2 equals 0. So lambda squared minus 4 lambda plus 5. Oh, great, it even factors. So lambda minus 5, lambda minus 1 equals 0. Really? We should have 1 and minus 1. I messed up a sign. Wait, no, I'm sorry. I was thinking. Never mind. I'm dumb. I was thinking of this matrix up here. Oops. This one. Yeah. Okay. So yeah. Our eigenvalues are 1 and 5. So we will have 2 eigenvectors. It is possible to have a repeated eigenvector or eigenvalue, and that's when linear algebra becomes terrible and ugly. But usually you have 2 different eigenvalues. So yeah, so we have the values. To get the vectors, we're going to return to this equation. Actually, I guess we're going to return to this equation here. I don't exactly remember how you can still get at least one eigenvector. It gets a little bit weird though. Find the function. Well, so we're about to find the vectors themselves. I don't really mean, or the function part, I'm not sure what you mean. Actually, I don't want that formula either. I want this one. So I'm going to start by taking lambda equals to 1. So we get, looking, 1 minus 1 is 0, 2 minus 1, 3 minus 1 is 2, times x, y is equal to 0, 0. And now this is just a system of equations with 2 unknowns. The vector x, y that we get out will be our eigenvector. In 0, 1, 1, 0, they were relying on the functions. Oh, right, okay. That's what we're finding right now. We are almost there. So I'm going to just make this an augmented matrix. Make life easier. I guess we're going to swap these 2 rows first. Then we'll subtract off row 2 from row 1. So we get minus 1, 0, 0. Is this even... Why does this feel off? Maybe it's not off. I thought we were supposed to get dependent. I thought they were supposed to be dependent. Wait, what? I'm gonna give Wolfram Alpha this matrix. I feel like I made a mistake. One, 2, minus 1, 3. Oh no. I don't know how to factor quadratics. Okay, that I chose a bad matrix. There's something else that can, so this is the part that I fucked up. This is not true. Yeah, so the other thing is you could have complex roots, which is also, it's not necessarily ugly, but it's a little less nice. 1, 2, 3, 4. Yeah, let's cheat and see if that one's a nice matrix. I want something a little cleaner. Okay, there. We'll use this one. 1, 2, 3, 0. Oh, okay. Okay, I'm gonna speed run through the determinant part, or through the eigenvalue part, because you already saw that. So lambda is equal to -3 and 2. Is that what Wolfram Alpha got? Yeah. Dancing in September. I made a sign mistake. It's 3 -2. Why? Oh, yeah, because I don't... Dude, I can't factor things. I'm washed up. Because it's like that, and then I just forgot to flip the signs. Ugh, okay. A minus lambda I times x equals 0. Yeah. Master student even. Okay, so starting with lambda equals 3. When will I evolve into Don double factorial? I don't know. It's a good question, Raven. Yeah, -2, 2, 3, -2. -3. Oh my god. 0, 0. Okay, and so this is what's what I expect. So like these rows should be dependent on each other, and this time they actually are. Like we should always have a row of zeros on the bottom. That's how I figured out that something went wrong with the last one. Plus 3/2 times 1. I think that zeroes out the bottom row. Okay, and so this top row implies -2x plus 2y equals 0. So we can choose any vector that fulfills this requirement. I mean, I'll simplify it down to y equals x. Oh, that's funny. Yeah, and that's right. So, ironically enough, we just got 1, 1 as an eigenvector. We're about 5 months out from the song. We are, Zach. Yeah. So that this is basically how you get your function out, Lucas. If we do the same thing for lambda equals -2, yeah, 1, 2, 3 is a much nicer matrix. I'm gonna do it for the other eigenvector just to get something that's not 1, 3, 2, 3, 2, 0, 0. Just subtract off row 1, 3, 2, 0, 0, 0, 0. So here we can choose, well, 3x plus 2y equals 0. Just going to solve it for y. Minus 3 over 2x. Right? Okay, yeah. So now we can choose any vector that fulfills this requirement. So if I choose 2 for x, oops, I'm going to choose 2 for x. That means y must be negative 3. But you could choose anything you want for x in either of these to get like the same type of eigenvector. And so that's why I'm saying, like, you can choose any scaling you want for these two vectors here, but these values are always the same. No worries. Whew. Hey, Sakno. Linear algebra? Hell yeah, linear algebra is such a great topic. Yeah, I was showing Lucas what an eigenvalue and eigenvector is. Oh yeah, that that takes the fun out of linear algebra. Summation should be avoided at all costs, I think. That's a heart that I can get behind, Benbox. Linalge, huge heart. And so yeah, there's another cool thing. So like in that other matrix, we got complex eigenvectors. And I think that means that your matrix is doing a rotation of some kind. Yeah, so you have like y equals 1 plus I times x or something. But yeah, it's like there's like the actually this is actually a special case of rotation. Well, actually, no, it's not. That's a reflection. Let me just Google it because I'm gonna get it wrong if I try to do it from memory. This is a good song. So yeah, you can choose any, if you want to just rotate all your vectors, you can choose whatever angle you want them to be rotated through and plug it into this matrix here. And I think if you did that and found the eigenvectors, they will be complex. So I think when you get complex eigenvectors, it means that your matrix is doing some type of rotation. It could also be scaling or reflecting or something else too. What is it in 3 dimensions? It's got to look terrible. Try and you look at the lotto one day. So if you want to rotate, if you want a transformation that rotates all your vectors by say like 90 degrees, you can plug in theta equals pi over 2 or 90 degrees into this matrix, and you'll get a matrix that rotates everything. This would be what? 0, -1, 1, 0. Can you also plug matrices into functions then? Um, yes. As long as the function is built to handle it. But I mean, I guess, yeah, you could do like, if you mean like y equals x squared, could x be a matrix? Yeah. It's hard to interpret, but it could. It's hard for me to interpret, at least. Oh, that's cool, Raven. The proud man counts his newspaper clippings, the humble man his blessings. Ooh. I think I've seen a version of that fortune in a previous cookie. It's a good one, though. If I had you, the money, fame, and fortune... Wait. If I had you, the money, fame, and fortune never could compete. That's a little awkwardly phrased, but okay, that's a compliment, I guess. You've gotten the cookie before? Maybe that's why it sounds familiar. I don't know. Okay, color cone. I think the fortune cookie is in love with you, Lucas. It's saying that if the fortune cookie was dating you, it would trade money, fame, and fortune for that. So there you go. You only have 39 coffee beans? Holy crap. It's not very many. It's a little more technical. Okay. You gambled everything? That's fair. Blue? You can sort of see it. It's a little bright, though. Something cool, I've noticed that B2, C1 English words are A1, A2 French words. What are the letters? What is B2, C1? You have 364K? Oh my god. I've done the convolution for the first term. Is it just this? You know what to make me draw? What a shame. A1A2 is beginner. Oh, okay, okay. Interesting. Yeah, I mean, Fenlox would just be guessing for the level of the game. He's already got VIP. Try to keep fee for the second one. Okay. Which is to commence, but more so used as to begin. Okay. He has everything. Use y as my integrating variable. Oh, for this one? Okay. I love that you have an emote. I'm missing the variable t. Oh, true. Sounds good, Lucas. Have a good night. Apparently, Fenvox does. I feel like Fenvox needs to have an emote here now. Like, where Shimmer had I feel like I'm in a competition for Fembox with whoever has that emote. Okay, you want to do... Okay. This isn't the original. I don't think, at least. So it's not the version I'm used to anyway. Sure. I can feel like combining them all into one big integral coming. Okay, yeah. I see the future. This feels kind of fucky. Are we factoring the y? The f of y? Yes, okay. This makes me uncomfortable so far, but okay. Triangle inequality? I assume a few times, or like as much as possible. Or actually, do we want it? Do we want it like this, or do we want it like that with a plus? The first one? Okay. Oh, and you're gonna say that phi is continuous, so we can bound it above by 0? Or not? Okay. Uh, centered at 0. Inequality? Oh, we're bounding f. I missed that. Okay. Maybe not epsilon. Maybe I like r more. Music stopped. Arm. Ah. Okay. Fundamental theorem of vector calculus to bound the integral. Really? I don't think I've seen the fundamental theorem. Vector calc. All right. Good night, Raven. Thanks for being here. Wait, the entire integral or... Okay, yeah, just the inside. Okay, okay. Huh. Oh. Just y. BXT. Oh, or that almost looks like a Taylor series. Like the first order. If it's come back support university contributions. We I'd expect there to be a t in the exponent too, but still not a big deal. It'll just change the notation a bit. That's the more like type of argument I was hoping to find. Let me keep following Collarcone's train of thought though. Music expression for phi. Compute grad x phi to bound that. Huh. Well, yeah. Okay, so the gradient shouldn't be that bad to compute here. They should all look the same, just slightly different. Whatchamacallits. So like for x1, we have an x1 squared, a negative x1 squared to worry about in the first entry. Negative x1 squared over 4t. I think I'm doing that partial derivative right. And all the others should look the exact same. We can bound the magnitude of y above by r as well. And when we take the magnitude of this, Oh wait, this doesn't depend on y anymore. Oh, ha, okay. So yeah, as long as the gradient of phi looks like a Gaussian, we're in business. Or like the magnitude of the gradient. I forgot the phi here. Ah. There's gonna be a square root though. I don't like there's gonna be a square root. It decays very fast in T. We still want like the leading order term though. Right. You're just saying you're just trying to bound it, I guess. Okay. Not necessarily do this actual computation. Shit, I do want to copy down what Pui said earlier too, just so I can think about that. Let me put it here. Um, about your worry? Okay. Pretend like I'm your therapist. Tell me about all your worries. um, the question as it is impossible. Well, that's a disappointment if that's true. The way the professor acts, he probably wouldn't mind if we put an extra assumption on this. He is not very precise with how he phrases things. Actually, just yesterday in class, students were trying to point out typos to him, and his only response was, figure out what I meant by it, basically. So how are you feeling today? Let's work on our goals. Yeah, exactly, suck now. In the argument, we assume U was given by convolution with a fundamental solution, right? uh, Gamaliel, thank you for the follow. Keep in mind the solution to the equation. It's not unique. It's distressing. I didn't know that. It's not unique. You hate Freud? Think of Tikhonov solution to f equals 0. You don't think a general solution will go to a Gaussian, as we've shown. I don't know Tikhonov. Nope. There are infinitely many solutions to problem 4.1. Remark 4.1? Definition 4.1? I assume it's just the heat equation. Okay. I doubt we're supposed to care about this, is my gut feeling. um, he's been pretty big on just trying to teach intuition and not proving things rigorously. We we probably don't have to care about that. Like if it's probably fine to assume that growth condition if that would fix it. Okay. Um, I'm still I am a little bit concerned with this magnitude of the gradient not being the exact thing that we want. Maybe we can bound it above by something else though. But then we've lost the Gaussian part. Don't like we need a Gaussian, don't we? But we don't care. Oh, because of our setup. Okay, we just want to show it goes to 0. Okay. Forgot about that. Just gonna call it alpha. Okay. So I'm returning back to this line. And then I guess we can slam in R times the volume. I guess we're writing a like magnitude of the ball, I think. The important thing is that those are all just constants. I guess so. I was hoping for something a little more like asymptotic, but I guess this works. It says like asymptotic, but I don't know. I really love my integration by parts idea, and I'm just sad it didn't work. I think. This still show looks like a Gaussian, I guess. Yeah. Thank you for showing me this though, color cone, because it is also good to see this. Like, I really need to get better with multivariable calculus. So even knowing that this theorem exists is good. I don't want to stream for much longer, but I do want to read a bit more about why do I keep getting scrolled? Um, because I do like what Pui is saying here because it's in line with we're talking about how um Gaussians kind of inherently scale with like root t in this heat equation context, and this makes use of that fact, which I like. I still need to kind of figure out how to go from each of these steps, but I do like this type of idea. Like a given path, gamma f of gamma 1 minus f of gamma 0 is equal to int grad f. Huh. Let me just look it up. I love calculus. Leibniz was Scientologist like monads. Can't be real. Oh, I was just watching Aristotle's stream. I forget what day it was, but it was like this week. And he was like power ranking different philosophers. And when he got to Leibniz, he was like, his philosophy is shit, his math is shit, who cares about calculus? And that made me really laugh. I know nothing about his philosophy other than like he talks a lot about monads. I don't know what monads are, but I know that's his big thing. This is, I think, basically the same thing as what you color cone. Fair enough. Okay. Physicist slogan: for conservative field, the work only depends on the starting point and the end point. True. Oh, and the gradient is always conservative. Is that it? It is, yeah. Oh, that's cool. Okay. Well, that makes perfect sense then. I didn't know that gradient f is conservative. Or maybe I have learned that, but it's been a long time. Actually, I guess I did, because I remember doing this potential function thing. And it only works when, like, it only works for a conservative function. So I guess I did learn it, but I didn't make this good connection. I do think I want to wrap things up though. I'm getting tired of thinking, as per usual, with these math streams. So metaphysics is that everything in the universe is made out of monads, atoms, and even reality is made out of monads. He was a very nutty individual, smart but very nutty. Makes sense. There's a lot of mathematicians who are very nutty. I think there's another mathematician who, like, he was good at math and he liked philosophy, but he was just terrible at philosophy. I forget who it was though. Like, even worse than Leibniz. Arnold was pretty harsh on Leibniz, saying it was stupid to think that dxy equals dxdy because that would be cool slash nice. Was that like, I assume? Oh yeah, Leibniz is the monads guy. Hey Papadoria. Uh, yeah, sure. If you can post it, I was about to wrap up the stream, but I'll stick around for a bit to look at your equation. Oh yeah, it's from your dreaded professor from last year. Kept giving you all the hard problems. Yeah, the same calculus Leibniz was also a philosopher. And a non-piecewise function f of x that abides by the following identity. 1 to the infinity? The LaTeX kind of died? Oh. Wait, yeah, this is not what you wrote, is it? No, it's not. What the hell? Oh, it's there's no underscore. Okay, it's a sum from n equals 1 to infinity of f of n. You just don't have the underscores. There we go. A non-piecewise function. Ooh. That's kind of cool. Uh, F equals 0 true max. That's a great response. Honestly, Pooh, I don't know what dx dot y would even mean, so... yeah, I'm sure that... I, I'm sure we want like a non-trivial. I mean, okay, so there's not that many types of functions that we know there's sum for. I'm worried that it's possible to do this without knowing what the sum is, which would make it much harder. But if we could restrict ourselves to like geometric series or like a P series, that could make this easier to think about. I'm worried that it's going to be a series that's more exotic, or that this is completely wrong. And that it doesn't need to be a series that we actually know the sum for. Trying to convert it into an integral, but it didn't work out. Yeah, I think you would need... I don't know what you would need. I'm always terrible at converting sums into Riemann sums. Um, Actually, it definitely cannot be a p-series because a p-series wouldn't converge in the in the integral. One over n equals one over x. But that integral doesn't converge though, Zach, right? Oh, I mean, I guess they both don't converge. They're, could you show that they go to infinity at the same rate? That'd be a funny argument. That's true. Hey Loki, I'm good. How about you? You show the uh con, non-piecewise means continuous. It does have to be continuous. It's good to hear, Loki. Huh. I assume it is. Um, or I assume it's trivial if it's piecewise. I don't know what the piecewise one would be. Oh yeah, that's fair enough. I guess tangent is allowed. Are you? Yeah, that's the the smart answer. Sophomore's dream. Let's Google that. Thank you, Zach. Oh, what? How do you prove this? Yeah, apparently. Yeah, I know about the. I've definitely heard of the sophomore dream, and I remember syntax. Oh shoot, that I feel like syntax error once asked me a question that was kind of like this, and Fizzbuzz uh tried to answer, and then he posted on Twitter, and someone on Twitter actually like solved it. I forget what it was though. I want to read the proof for this because this is wild. Chilling in Chennai. That rolls off the tongue. Yeah, let me put that in YouTube chat too. I know about Chennai from chess because they have chess tournaments there. Uh, King Gears proof x to the x equals exp x ln x. Wow, I can't believe a Wikipedia article is actually explaining this. It's rare. Whoever edited this Wikipedia article is a kind soul. Oh, really? It is rare. Yeah. Oh my god, that's not an easy substitution to find. You'll fix all algebraic notions in Wiki? That you be doing God's work. What? Oh my god. It does become the gamma function. It was originally done by Bernoulli. Yeah, it's so smart looking at what it gives you, but I would get so stuck at this stage. But it makes perfect sense once you realize it gives you the gamma function. Um Wait, does it make sense? Yes, because it cancels. That's crazy. It is. Yes, and they engineered a substitution that gave them the definition of the gamma function. How did Bernoulli do it? Oh, the gamma function hadn't been created yet, but he figured it out intuitively. Okay. So why is this a dream? Oh, it's too good to be true, but it is true. Whereas the freshman's dream is too good to be true and is not true. Okay, that's kind of weird. Louis, I you're just better at integration than I am if it's not that hard. Like I understand it, like if you gave me the steps I could definitely execute these steps. Like that part isn't that hard, but spotting this substitution, if you were doing this, if you're Bernoulli and you're the first person to do this problem ever, spotting that from nothing is really smart. And Bernoulli didn't do exactly that substitution, but he may as well have. Sounds good, Loki. Thanks for saying hi. Yeah, exactly, Dustin. It's even harder if you don't know what the gamma function is, like Bernoulli did. But hey, Papador, at least on the bright side, this isn't the Collatz conjecture. Like, imagine this was just some wild thing that reduced to being the Collatz conjecture again. To know the right side was almost routine, yeah, I agree with that. Time for a Destin TED talk. I would watch that. Oh yeah, look, this is like if you did like a year's worth of calculus, you would know enough to understand this. He never does that again. You're stuck all night on it. Yeah, that was that was such a funny moment in the stream. Did it make you understand what a scheme is? Oh God. I didn't even see that Dustin challenging color code to give him a definition. If there are other known functions that fit this, I don't know. Maybe. The integration with the uh integration exams should be with the U sub given. Honestly, depending on the integral, yeah. Probably for a harder integral. But I think an exam should be able to test you a little bit on finding the use of for yourself. Cantor? Ooh, that's a good choice. I don't think he was a messed up person. Choosing a special or choosing like a favorite mathematician is usually kind of dangerous because you find out that they were like just a terrible person. I don't think Cantor's a bad person though. Ooh, that's a cool signature too. I really like looking at the signatures on Wikipedia. And Cantor's a cool one because like his work is really important, but at the time, like people did not believe him. He wasn't appreciated until like towards the end of his life. Do you know the x and y plane? Think of each axis as an ideal. There you go, a scheme. I understand it perfectly, Dustin. You did it. I definitely know what ideals are. He was a terrible person. Very sad. People thought he was crazy. Yeah, Veritasium has a really good video about Cantor, where he actually like animates um like imagined versions of some of these scenes. But let me find it. 'Cause it's a really good video. I want to link it. One second. I don't know why I'm hiding the screen. There's not really a point in hiding it. Veritasium. Uh, it wasn't that long ago. I thought. Feel like I scrolled past it already. The axiom of free will. It's gonna bother me. I forget what the name of the video was. What? Will this bring it up? Wait, did he change the name of the video? He did change it. That's why I couldn't find it. Okay. That's the one though. I really like this video. And it's all about Cantor. Well, yeah. Okay. I do think that's going to be the end of the stream for today. When I read into it, I felt very much the same thing, specifically me talking about mathematics and voting methods, pointing out their flaws, helping me understand in personal sense. There's a system of choice higher than what we can formulate. Oh, nice. Suck no. He changes thumbnails every 10 minutes too? Yeah, he does. Okay. As I said, that is it. Papadoria, Ayush, anyone else who's here on YouTube, thanks for being here. on Twitch, I'm going to look for a raid. Papadoria, thank you again for the question. And yeah, I'll see you later, YouTube.